when doing parametric equations, the third variable, like again, we're going to do by an example here, is oftentimes time. And time becomes things that like talk to us about what's happening. So in this example, pardon my poor handwriting, but because I get to speak, I can tell you what it says. It says write an equation x of t. So x in terms of t. We've done other equations in the past, like h of t, height with respect to time. So x with respect to time, if it takes 4 seconds to travel from A to B, and then we're also going to create an equation for y of t as well. So basically, I'm starting here. I'm going to travel from here to here in a straight line fashion for now. Well, that's really not a good straight line. It's directional because I'm going from A to B, so sometimes having an arrow on there, but indicating an ending point of B. I need to come up with an equation to talk about how x changes. So x of t. Much like you've done in the past, you're thinking, for this part anyways, y equals mx plus b. So either my pen is dying on me, or I'm not pressing hard enough on my, there we go. All right, y equals mx plus b. And my change in x over time. So I look at my points, I say, all right, well, from A going to B, I'm going to change from -5 to +3. So my x is changing a grand total of 8 out of 4 seconds. So my slope, if you will, for x of t is 2t. All right, and then, but I got this b. I said we're thinking like slope-intercept form, but it's not purely slope-intercept form. If you think back to slope-intercept form, when you put 0 in for x, it would tell you that y equals b, and that would be the y-intercept. But I'm not doing a y-intercept. I'm doing a when t is 0. When t is 0, what is my, in this case, x of t? At time 0, I am starting at -5. So it's 2t minus 5. That is my equation for x of t. All right. And that, again, what does that equation describe? That equation describes the location of the x coordinate over the time period of 4 seconds as it travels along this line segment. And then to find my y of t, I look at my y coordinates. How are my y coordinates changing? They're going from 3 to -1, or a grand total change of -4. So that's my delta y, my change in y, divided by change in t. Change in time is 4 seconds times t. And then it will be plus 3, because at time 0, the y-coordinate is 3, because that's my starting point at point A. And I'll just rewrite that equation a little bit nicer. Y of t is equal to -t plus 3. So in terms of parametric equations, this scenario, where I'm going to be looking at creating 2 equations for the position of x and the position of y with respect to time t from point A to point B, is modeled by this equation down here for y of t equals negative t plus 3, and this one, 2t minus 5. All right, that's our little introduction. We're going to work through then several examples today to solidify some of this and what it looks like, and then we're going to actually go back and forth where sometimes we're going to be given parametric equations, and then from that we have to find the Cartesian, and sometimes we have the Cartesian and we're going to parameterize it. One word to say. All right, so now we're going to have two polar parametric equations, and I wrote an extended t-table. Remember doing that way back in the day? Pick some convenient numbers and you work your way through, and then you find the corresponding values and we plot them as we go. That's what we're going to do. So we're going to start with the beginning. So when we're doing it for a polar coordinate system, so I have x of t is equal to 2 cosine t, which is a circle all by itself. X is r cosine theta. All right, so all by itself, that would be a circle with a radius of 2. All right. The y all by itself would be a circle of radius 4. But then what are they if they're actually the parametric components of some broader parametric equation? That's what we're going to figure out. Working on the unit circle, we almost always start like where we would at the very beginning at 0 degrees. So we go, all right, what is cosine at 0 degrees? That's 1 times 2 is 2. So again, as you're looking at that, cosine of 0 is 1. 1 times 2 is 2. Y of t is, what is sine at 0? Sine at 0 is 0 times 4 is 0. My point is going to be at 2 and 0 for my x and my y of t. Then pick another equation going up. Not equation. Pick another theta, another value, another angle. I mean, you could go through all of these if you wish, but we'll pick ones that as just a good habit here. So at pi fourths, cosine at pi fourths is square root of 2 over 2. Cosine of pi fourths is square root of 2 over 2. Times 2 gives me square root of 2. And then my y coordinate, my y of t, 4 times sine of pi fourths. Sine of pi fourths is the same thing, square root of 2 over 2. Times 4 would be 2 root 2. So if I call this 1 and this one 2, just so we have space. So this is 2 over. My first point was going to be at 0, 2. Nope, so I'm up 2. 1, 2. My second point is at square root of 2 and 2 square root of 2. Oh, hold on a second. It's 2, 0. 2, 0, right there. And then square root of 2 and 2 root 2. So square root of 2 is a little over 1. And you might be thinking, how is that on a parametric? We're going to get there. We'll actually bump over to Desmos at some point in time and plot this and show you how it works. But we'll just keep going and putting a couple more points in here. Let's do pi thirds. Cosine at pi thirds is a half. Times 2 is 1. Sine at pi thirds, square root of 3 over 2 times 4 would be then 2 square roots of 3. Pi halves, cosine is 0, sine is 1, we're at 4. 1, 2, 3. Oh, I ran out of room on my graph. I should have done it more like this. And you keep working your way around. What we would actually find if we were to connect all these points is that I'm going to have a very terribly drawn, but an oval of sorts. All right. Officially, we'll call it an ellipse. So if you're given the two parametric equations, you can make an exaggerated or a augmented t-table, having your t as my original points. So at time 0, and then as time goes on, what's the function going to do, and where's that point going to be, and how is that going to be described by each of the x of t and y of t values. All right. So then this, I have a graph that's in t. So this is the x, where x is with respect to t. Here's where the y is with respect to t. And for something like this, I would say, hey, graph this in an xy plane. So it's going to be the same kind of thing. We're set up t, x of t, and y of t as a table. And then find out what those coordinates will be. And then eventually what we'll do is we'll grab these points and then plot them. So if I do that, so at 0 for time, here's time of 0. My x of t is 1, because I can see it reading it right off the graph. And at time 0, my y of t is 4. So this will be 1, 4. So when I go to graph it, that's what that point will be. All right, picking some other numbers. So it goes, maybe I should have put that in the middle. So let's go -3, -2, -1. So at -3, it looks like x is at about -0.5. At x is -2, at t is -2, x of t is at -2. 0. It's at 0. At t, I would do x. At t is -1, x is at +0.5. Hold on, I'm getting some things here. Let me get back to here. I do into my x's and then I wasn't looking at my y's. Where was I? Back here at -3. My y is somewhere down below. It's going to be a large negative number, possibly negative, I don't know, can't even guess, so I'm not going to put it there, but it's going to be a very negative number. At -2, the y of t is also 0. At -1, I said my x was +0.5, and my y of t is +3. And then at 1, 2, 3, my y looks like it's symmetric, so y is going to be 3. At 2, it's 0, and at 3, it's very negative again. And my x at 1 is 1.5, which I'm going to write as 3/2. At 2, the x is at 2. And at 3, my x is at 2.5. 5/2. Now, if I were to recreate this, I'm just going to do this graph, call this x now. And this is now going to be my y values. And then I'll plot my points. So at 1, I'm at 4. At -0.5, I am at is very, very negative, so we'll leave it there. I'm at 0, 0. At 1/2, I'm at 3. At 3/2, I'm at 3. At 2, I'm at 0. At 5/2, I'm very negative. So at -1/2, I'm way low. At 5/2, I'm really low. What does this look like it might be? Looks like it might be a parabola, something like this. Ooh, I missed. Like that. So that's how, when you're given two graphs, it takes a little bit of time, but you can piece it together, look at your t values, what are the corresponding x's and y's, and then plot it on an xy plot. All right, so then it's a matter of saying if I have something in polar, not in polar, parametric. How do I convert it into Cartesian? What you're going to think of when you're doing these is think of the x of t just as a plain old x. Because eventually it will be. So x of t is just going to be an x. So I have x equals 2 cosine of t. And with sine and cosine, if I can get something and get them isolated, if you will, what do I mean by that? So divide both sides by 2. So x over 2 is equal to cosine of t. I'm going to leave that one there. I'm going to take a look at the other equation, y equals 4 sine of t. So y over 4 is equal to sine of t. And then the reason why I do this is I'm thinking to myself, do I know any kind of a relationship that includes sines and cosines? Like if I knew something about sine, knew something else about cosine, could I put them together into a giant equation that equals something? The answer hopefully is yes. Sines and cosines, it's our favorite Pythagorean triple. Sine squared of theta plus cosine squared of theta equals 1. So here we have t instead of theta, but it still works. So sine squared plus cosine squared equals 1. Or what I have is y squared over 16 plus x squared over 4 equals 1. And what that actually is, that we'll be doing a little bit more time with the next chapter, is that's a ellipse. It's an ellipse, and my long axis is in the y direction, and my short axis is in the x direction because the number under the y value is larger and the one under the x value is smaller. So it would be similar to the one that we just did. Actually, were those the numbers that we just did on the other equation? It was, wasn't it? Those were the same two equations. So it's going to be an ellipse just like what we saw, where it's from the center, it's 4 units up and 4 units down, which is the square root of the denominator. And in the x direction, it's 2 units to the left and 2 units to the right, which is the square root of the denominator under the x. And that is the relationship that they have. They'd be called r1 squared and r2 squared when we get to actually doing an ellipse. But in terms of looking at parametric equations, if they have sine and cosine, if you can isolate the sine and isolate the cosine, then you can say, yes, because I remember sine squared plus cosine squared equals 1. What if it's not sines and cosines? If I just have something like this, how can I convert it into a Cartesian set? I would do it like I said before. Consider this and just think, well, this is x equals t cubed. And what we're going to do is solve for t in one of them and then plug it back into the other equation. So my t is equal to the cube root of x. I just took the cube root of each side. Well, if I can do that, then I can take this number, this thing, and swap it into there for the t in replace of t. So I'd have y equals the cube root of x to the 6th power. And this is where I prefer, and you might find yourself getting in the habit of, instead of writing it as x cubed, writing your roots as fractions. All right, so cube root is x to the 1/3, because then when I do this on the right-hand side over here, I'll have y equals x to the 1/3 to the 6th. And then I've got my powers raised to powers property of exponents. Y equals x to the 6/3, which is x squared. So the equation for the parabola y equals x squared that's centered at the origin as a parametric equation is this. All right. When we switch from Cartesian to parametric, it's called parameterization. I couldn't find the word, so can you Cartesianize it? Like, I couldn't think of a way to do it with the way the words are. But again, this is the same one. We have two parametrics. We're going to convert it into Cartesian coordinate system. This one I'm going to sit down with just because it's a bit more involved. There's two ways to do it. I'll actually show you both ways as we go through it. So I'm going to start with the one on the left, and I am going to isolate my t by having x minus 2 equals the square root of t. And then I'm going to square both sides. X minus 2 squared equals t. And then I will take that and plug it into the other equation. So my y equation will now be y equals the log of x minus 2 squared, or, and it's both are equally the exact same right number, or right equation I should say, 2 log of x minus 2. Either one of those would be a permissible way to finish out that problem. That's not the only way you could do it. Now, the next way I'm going to show you is harder, but it illustrates some of the points of logarithms and exponents that are going to be on the exam, so I figured why not show you how you can have one question that captures many aspects of many chapters all in one, but this is how it would go. We're going to take the other equation and we're going to solve it. So this is y equals log of t. Recalling that a logarithm is an exponent is a logarithm. Standard logarithms are base 10, so I can take a logarithm and I can rewrite it in exponential form. It would be 10 to the y power equals t. That's how a logarithm converts into an exponent. And vice versa, if I have something in exponent form, I can convert it directly into a logarithm. But now I know what t equals. So in the other equation, I'm going to swap it in. So x equals t, which is 10 to the y power, square rooted, which is to the 1/2 power, plus 2. All right. And then properties of powers. So eventually I want to have an equation down here that's going to be y equals something. And my y is in my exponent. So I'm going to move the 2. And this will equal 10 to the 1/2 y. Powers raised to powers. You multiply the powers. Y times 1/2 is 1/2 y. And now I need to get my y out of the exponent. And to do that, I take the logarithm of the base of whatever the value is that's the base. So this is a 10, that's my base. I'm going to take the logarithm of both sides. So when I do that, I'll have log of x minus 2 equals log of 10 to the 1/2 y. The exponents inside logarithms can come out in front. I'll have log of x minus 2 equals 1/2 y times the log of 10. And the log of 10 is saying 10, think about how it was up here in exponents. 10 to what power is this value? 10, the base, to what power is 10? Or if you plug in your calculator, log of 10 is 1. They are inverse operations. Just like when you say 2 divided by 2, that's 1. Log of 10 is 1. Natural log of e is 1. Log base 2 of 2 is 1. So this is 1. I'm left with 1/2 y equals log of x minus 2. Multiply by 2. Y equals 2 log of x minus 2, which we had on the other slide. which could also be rewritten as y equals log of x minus 2 squared. So now we're going to parameterize this equation. You might be thinking, oh, I hope this isn't this is actually the easier part. I need to have a t, and I need to have some relationship between a t and an x. And it depends on how you want to put it in there. I could say let y equal t. So then I would have x equals t cubed minus 2t. So x of t would be t cubed minus 2t, and y of t is t. If you did it the other way and tried to do let x equal t, then you'd have a lot more work to try to do, because then you'd have t equals y cubed minus 2y. You'd have to somehow find a way to solve that for y, so you'd know what the value of y is with respect to t. That's a lot of work. So if they give it to you and there's just a quick and easy, like, oh, this variable is all by its, or this one's the more complicated one, just go with that. I'm going to let my y then be my t. So as soon as I do that, now I've got x is then t cubed minus 2t. It's not honestly going to be a whole lot harder than that for the problems that we're going to have to face and see. So don't, I'm not like bait and switching you to show you an easy one and then give you something monstrous. This, however, is a little bit more monstrous. So this is the kind of the end goal of what this might look like. And after this, then I'll throw up some Desmos and we'll look at what this actually looks like when we graph this all out. So my scenario is the moon travels around a planet orbiting every 10 days with a radius of 6. Obviously, this is very fictitious because 6 doesn't even have units on it. But for the sake of how to make this problem like reachable, that's what we do. The planet itself travels around the sun, orbiting every 100 days with a radius of 30. So imagine this, if you will. You got your circle of this planet. Oh, and we're going to assume a circular orbit. Again, truly false, but it gets a lot more complicated if I have to take a sinusoidal curve and throw it around an ellipse. Not impossible, but beyond what we're going to have to work on in a class like this. So we're going to find the parametric equation for the position of the moon relative to the center of the sun after a certain number of days. So parametric, so I'm thinking x r cosine theta because I'm dealing with all these things that are traveling in curved patterns, right? Circular patterns are going to be traveling around. So r cosine theta, y is r sine theta and r cosine theta. So x of t is going to be the same thing, but then recalling this is my general formula for a sinusoidal curve, where a is my amplitude. When I do it like this, it's my radius. So for my x of t of the moon's radius is 6. 6 times cosine of b. Recalling, b is equal to 2 pi over a period. So I have 2 pi over 10. Because it tells me that it does a full orbit in 10 days. All right. We don't have any horizontal shifts. There is no h. Oh, I forgot my general formula up here, the actual value. Oh, no, theta's in there. Never mind, it is. Okay. And then I need my variable. And my variable in this case is going to be t, end parentheses. And has it told us anything about a shift up or down for k? No, there's not. That is my x parametric function for the position of the moon traveling around the planet. Y of t for the moon, 6 sine 2 pi over 10 t. Or I can simplify this as 6 cosine pi fifths t. And this will be 6 sine pi fifths t. For the planet, same idea. X of t equals 30. That's my radius. Cosine of 2 pi over 100 for the 100 days to complete a full travel. So that will be equal to 30 cosine pi 50ths t. Y of t, 30 sine pi 50ths t. And if I want just the relative position of the moon with respect to the sun, that's what it says, find the parametric equation for the position of the moon relative to the center of the sun. That would be the position of the moon and the position of the planet together. And it actually ends up being, so I'll call it x of t combined, would be the sum of the two. 6 cosine of pi fifths t plus 30 cosine pi 50ths t. And the y relative position combined parametric equation with respect to time is the combining of those two. 6 sine pi fifths t plus 30 sine pi 50ths t. Or if I'm thinking about this as an actual graph, then it would be this as my x coordinate, this is my y coordinate for the position of the moon as it orbits around the planet, as it orbits around the sun, and t is the number of days. So now, let's remember what that is, and let's see if I can type that into